So as I mentioned, the torque produced by the motor, if we have a single armature, is essentially equal to the number of turns in the armature, the flux produced by the permanent magnets, the current flowing in the armature, and then we have sine omega mt. And similarly, the back EMF that's produced is n phi f times the angular velocity sine omega mt. So my point here is both are function of time. So in reality, we are not going to use one armature. We use multiple armatures, or what we call multiple phases. So as instead of using one armature, we're going to use multiple armatures. In this case, or in this figure, we have two armatures, but in reality, we're going to have many armatures. And eventually what we will see is, instead of having the torque as a function of time, we'll find that when the torque produced by one armature is going to zero, the torque of the other armature is reaching peak while this one is in between, and so on. So we'll find that the torque is becoming constant versus time essentially. So instead of having the torque as a function of time, what we'll see is in multi-phase DC motors, we see that the torque approach a constant value equal to the peak of the sine, which is equal to n phi f ia. And also we'll find that the back EMF, instead of being a function of time, is going also to approach a constant value. And lastly, we'll see that the current that's taken from the source is basically approaches a DC value, I capital A. So we can replace this I by I capital A. And generally we take the number of turns times phi f and we call it the motor constant, capital K. And similar in the back EMF as capital K omega m. Alright? So now we can find the equivalent circuit of a brushed DC motor. As I mentioned, we are going to have the equivalent resistance of the motor as the armature, its equivalent inductance, then the internal back EMF, EB, where EB for a multi-phase brush DC motor is equal to K times omega m, where omega m is the angular velocity. One point that I would like to clarify here. Now we have current that's flowing IA, and of course we have a DC source here that will produce this current. Now if we look at the mechanical power produced by the motor, we said it's the product of the torque, produced torque times the angular velocity of the rotor of the motor. We'll find that this is going to be equal to the electric power provided to the motor. And we'll see that the amount of mechanical power produced by the motor is actually equal to EB times IA. EB is the back EMF or back electromotive force times the applied current IA. Why? Well, let's expand this expression. We have the mechanical power is omega m times the motor torque, and the motor torque is basically K times IA. And we said the back EMF is also K times omega m, so it will be EB times IA. Alright. Another point is, what is the value of the armature current at steady state where there are no variations, no transient operation? The inductor will essentially going to behave as a short circuit. So this equivalent circuit of the multi-phase DC motor will boil down to this simplified circuit. This is VDC, this is EB, and so the value of the armature current IA at steady state is going to be essentially the applied voltage minus the back EMF divided by the armature equivalent resistance RA. Now, let's take a look at an interesting point in the about DC motors. Let's see the torque angular velocity relation, or essentially I want to plot it. I want to plot the relation between the electromagnetic torque produced by the motor and its angular velocity. Well, from the equivalent circuit that I just plotted, we said that EB is equal to K, the motor constant, multiplied by its angular velocity. Under steady state operation, we can ignore or replace the coil or armature inductance, equivalent inductance, by a short circuit. Then we have the applied DC voltage across the DC motor, and then we have its DC current IA. Now, if we look at the torque, we said the torque is what? Is equal to K times IA. And IA from this circuit is equal to VDC minus EB divided by RA. And EB is given by this equation, so we have K times VDC minus K omega m divided by RA. Now, this equation provide the relation between the torque and angular velocity under steady state operation. And if we look at it, this looks like Y is equal to some constant E times another constant minus slope. Well, this, essentially I mean here a constant because we have a factor E in outside, times X, which basically a straight line with a negative slope. And when omega m is equal to 0 from this equation, we'll have the torque is equal to K times V. Let me sketch this again. And let's write the equations as the torque produced by the motor, or the electromagnetic torque, is K times VDC minus K times omega m divided by RA. And so when omega m is 0 at this point, we'll have the torque equal to K VDC divided by RA. On the other hand, when this point essentially will happen when the torque is equal to 0, and when we solve this equation, we'll have it as K VDC, or sorry, is going to be equal to VDC divided by K, right? If we put the torque here equal to 0, and the VDC minus K omega M divided by RA, so omega M is equal to VDC divided by K, which is this value. So what does that mean? Well, let's imagine two scenarios. This is our motor, and in this motor, in our motor, scenario 1, we connect a small mass across the shaft of the electric motor. Say we put 10 kilograms of load, okay, of mechanical load, and we take the same motor. In scenario 2, we connect 100 kilograms of load. Obviously, the mechanical load here in scenario 1 is going to introduce a smaller load torque than the 100K. So the 100K is going to produce larger amount of torque load than the 10 kilograms case. Rotating the 10 kilograms requires a smaller amount of torque than rotating the 100 kilogram load. And so scenario 1, let's put them here in this domain at steady state. For the 10 kilogram, which is case 1, rotating it requires a small amount of torque, while for the 100 kilograms load, it requires a large amount of torque. So this is scenario 1, and this is scenario 2. In both cases, this curve is plotted for a specific VDC value, because a specific VDC value will set this point, the intersection with the y-axis, and also the intersection with the x-axis. So for a specific VDC, we are studying essentially both load cases 1 and 2. For 1, essentially it requires a small amount of torque, so the speed, the angular velocity at steady state of the motor will be at high value, omega 1, m1. While for the second case, when we have 100 kilogram, it requires this load, larger load, 10 times larger load, will require a 10 times larger torque, you may say. And so basically it will produce a steady state angular speed that will result in case 2 will be much smaller than case 1, right? So now, if we say we have this motor and say an electric car or whatever, a toy car, because we're studying brushed DC motor, and as toy car essentially is moving and controlled, it might face an increasing surface or decreasing surface, so we can't have a constant VDC across the motor. We need to control it. So how do we control the speed if we want to maintain constant speed for the toy car? We need to change VDC. So for example, in say we want the motor, the electric car, to essentially move at a specific speed, such as that the angular speed of the motor is omega m2, and we want to maintain that under different load. And suddenly, essentially, after the car was going up the surface and facing large mechanical load, it goes to flat surface or even decreasing surface, that essentially the mechanical load goes to case 1 or very light. So the motor want to increase the speed for the same VDC value, but we're going to do to maintain essentially the speed of the motor constant, we're going to reduce the value of VDC. So when we reduce the value of VDC, this intersection point is going to decrease, such as that the new line is in here, and we maintain the same velocity under different loads as the toy electric car is moving and being among different surfaces that impose different mechanical loads or require different amounts of torques.